Now we're going to introduce a formal definition for electric flux. And as it shows right here, our formal definition is based on dot product. So we have a mathematical tool in dot product that will always result when we take the dot product of the electric field and our area vector A will result in the electric flux through that area A. Now, the first thing you want to do when addressing flux is to identify the n hat vector that goes with the area A. And that's the first thing you want to put into your notes. So get this n hat vector in here, perpendicular to our area, which in this case I used an example area of 2 meters by 5 meters, so a rectangular plane, and I stood this plane up so that we're looking at the same perspective here in the YZ plane. So you can get the YZ plane in here, and X is to, positive X is to the right. And if we are not given the direction of the n hat vector, by convention, it is chosen to be in the positive x direction, because if we note here, we could have made it perpendicular and in the negative x direction, but by convention, it's in the positive x direction. And now we're going to see the usefulness of that n hat vector. So let's take a look, a little closer detail for our mathematical definition. Well, the example that I have shown here is looking at just a general electric field. I've added some numbers, so just a general electric field, so get this in, of 20 newtons per coulomb at some angle theta equals 40 degrees. So get that into your notes. And what we're looking at is what electric flux from this electric field is going through our area here. So how much of the field actually passes through the area. Now, if you recall from our conceptual definition, what we're interested in is the electric field that goes perpendicular through the area, not the electric field that rides along or is parallel to the area. So E parallel does not contribute any flux, only E perpendicular. And this is where dot product comes to our mathematical rescue. We don't even have to think about it. If we look at the flux based on our definition of E dot A, so let's take a look at E dot A. So here, the dot product automatically introduces this cosine of theta. So you can see that cosine of theta here is the same cosine of theta that we need to calculate our E perpendicular. So there you have it. All we utilize is our dot product. When we go into dot product mode, we get magnitude of the first, magnitude of the second, cosine of theta, the angle between the vectors as drawn from a common origin. So notice the 40 degrees is my angle theta as drawn from a common origin, my n hat vector. And let me bring my E vector down a little further. My E vector down here, that angle in here is the 40 degrees that we need. So dot product takes care of it for us. So we get our magnitude of the first, magnitude of the second, cosine of the angle between the two as drawn from a common origin. And notice cosine of 40 degrees, it isn't just a number, it's going to be positive. So cosine can be positive or negative. It'll be negative when we go from 90 to 180, and we're going to get that into our notes so that the flux is positively valued when the electric field passes in the same direction as the n hat vector. It'll be negative when the electric field, the flux part, the E perpendicular part, opposes the direction of the n hat vector, and that's where we get our negative. So we have a great mathematical tool in dot product to allow us to mathematically calculate the electric flux. We have a couple of examples on the next 2 pages for you to look at, and we'll go through those solutions as well.